Hello everyone. Today's lecture we are starting electro-optic modulators for integrated photonics. So, this is an important component for photonic integrated circuits. So, we thought of discussing starting from the basic design and what is the working principle. So, step by step we will be discussing on modulators for high speed data encoding, where it is being used today, particularly when you talk in terms of photonic integrated circuits. And then there are two types of modulators popular. One is phase modulator, that is eventually a frequency modulation, and then finally amplitude modulation or intensity modulation. So, let us see how a modulator play a major role in high speed data encoding. So, here I have tried to give an example borrowing photograph the scheme from Intel Labs white paper. This was depicted in 2010. So, when they actually demonstrated the world's first silicon photonics data connection with integrated lasers. 50 gigabit per second silicon photonics link. So, before that actually high speed modulators being used for long haul optical fiber optic communication, but the modulator mostly dominated by lithium niobate modulator. So, this is the first time silicon photonics modulator fabricated using CMOS technology and tested how that is tested the performance of those silicon photonics modulator using fiber optic communication link. So, here for example, it was shown that the communication is taking place between two chips. So, chip 1, that is actually nothing but your transmitter, and then chip 2, that is actually your receiver basically. So, that is what it is said that integrated transmitter die. So, it is fabricated for example using CMOS technology. So, there are 4 different color shown here. They are basically laser. They are emitting different color, different wavelengths. Why it is hybrid? Because as you know, silicon platform is not at all good, particularly silicon material is not at all good to demonstrate laser diode, and because of its indirect band gap. So, mostly even though if you give a forward bias to a diode, silicon diode with maintaining all the condition required for a laser, but you do not get really photoluminescence or photon emission, because the population inverted electrons in the conduction band that actually relaxed to valence band through different ways with a phonon assistance is required for that, and that actually eventually blocks the laser emission possibility, photon emission possibilities. So, that is why hybrid laser means it is laser, normally it is fabricated using 3-5 compound semiconductors. So, those lasers were fabricated separately using 3-5 semiconductor, for example, indium phosphide platform, and they were actually mounted on silicon chip. 4 different type of laser as I mentioned. This can be considered lambda 1, lambda 2, lambda 3, lambda 4, and each of this lambda laser emission, it is fed into a modulator, so called electro-optic modulator, where your data can come and the data can be encoded with this laser light having wavelength lambda 1, and similarly lambda 2 another data stream can come and that can be modulated again with another modulator, and lambda 3, lambda 4, so on. So, each of them actually can encode data up to 12.5 Gbps. So, 12.5 Gbps times 4, it is actually 50 Gbps transmitter. So, in the background you can have your electronic circuit, driver circuit, where actually you can make all the data stream parallel to these modulators. You can divide them into 4 modulators, and since they are actually encoded into 4 wavelengths, you can use a multiplexer, wavelength multiplexer. So, normally you know they are very popular, it is used in fiber optic communication, dense wavelength division multiplex system, DWDM, where actually for high speed data connection, it is more than 160 number of channels could be multiplexed together. But in this case, for silicon photonics transceiver, here it is multiplexed 4 channels. So, that is why this wavelength separation can be wide enough, 8 to 10 nanometer and so on. So, 8 to 10 nanometer separation, lambda 1 to lambda 2 and lambda 2 to lambda 3, lambda 3 to lambda 4, and you can multiplex them, and you can feed into a fiber optic cable that can be single mode and multimode depending on the requirement, how much distance you are actually transmitting. And then at the receiver end, when it is received, you can again demultiplexed depending on its color. So, this lambda 1 will appear here and lambda 2 will appear here, lambda 3 will appear here along with its data encoded. Okay. And then you can use a photodetector there. Photodetector basically actually demodulate or decode the data, that means it converts the optical data into electrical data. Same way lambda 2, lambda 3, lambda 4, 4 different photodetectors can be used, and all these photodetectors actually should be made suitable so that it can detect efficiently in those wavelength. Okay. And then you can reproduce your electrical data stream. So, that is how actually modulator plays an important role for fiber optic communication. And earlier days these modulators were fabricated, as I mentioned, it is a bulk, it is an integrated optical modulator though, but it is a standalone modulator, high speed modulator, that is in lithium niobate. So, these are the first time demonstration modulator, high speed modulator at least 12.5 Gbps using silicon photonics technology. Okay. And so, not only that, actually this, because of this advancement of silicon photonics technology, as I mentioned in the beginning of this course, that people were trying to replace the electrical interconnects with optical interconnects just to get rid of bandwidth limitations. So, here is one depiction that how a optical modulator or silicon photonics technology can be utilized for on-chip communication. For example, you can use a laser that can be off-chip or can be hybrid integrated on silicon photonics platform, and then you have a silicon modulator where you can co-integrate electronics driver, and that actually feed into your electrical logic cell, whatever data is coming, the driver can be conditioned, driver can condition the levels 1, 0 levels, and then you can actually feed that data stream to optical modulator, and then you can just, instead of fiber, you can just directly launch into a waveguide, and the waveguide can carry the optical signal encoded with all the data stream that can be guided. Low loss waveguide can be fabricated on silicon photonics technology platform, and you can take them, guide them wherever necessary, and you can detect, demodulate the optical signal, and you get the electrical signal back, and you can amplify, and again you can feed into another electrical logic cells. So, in this way you can actually integrate together the optical modulator along with the waveguide or all other devices, and then you can try to replace electrical interconnect wherever necessary, wherever bandwidth limitation, with the optical interconnect. Okay. If you want to know a little more, then I request you to go through this paper by Haurialu et al. The title of the paper is On-Chip Optical Interconnect Roadmap, Challenges and Critical Directions. So, that was the first time it was demonstrated in 2006, that is long back, around 15 years ago. Today we see that lot of photonic integrated chip available commercially, so based on this concept now. Okay. So, now let us try to see that what are the modulation parameters for a guided mode? What you can modulate? One thing you can modulate your amplitude and phase, as I mentioned before, but how that is mathematically you can actually model that. Let us take an example of a waveguide cross section of silicon waveguide cross section. That is normally we know that the waveguide cross section and the parameters are design parameters are W, that is waveguide width, and device layer thickness, and you can have your slab about small h according to the requirement, and this can be designed W, capital H and small h you can suitably choose for single mode guidance if necessary. And if you see, even if it is a multi-mode or single mode whatever, mth mode distribution, we have shown earlier that it can be described by this type of formula as long as orthogonality condition maintained. So, the mode profile of the mth mode, that is actually the eigen solution, and beta m is the propagation constant, is the eigenvalue solutions also for that mode. And if the waveguide is propagating along z direction one dimension, we can express like that, and amplitude am depends on how much energy, how much power encoded power associated with the guided mode, mth guided mode. And one more parameter we have, that is actually the polarization of the electric field, because you know electric field, electromagnetic wave or light wave, when it is guided through a waveguide structure, then it can have all three components Ex, Ey, Ez. Okay. So, considering this thing, if Ex is dominating and Ey close to 0, then it is called T-like mode, and if Ey dominates and this is close to 0, then it is called Tm-like mode. So, but many times you will be seeing that your solutions giving both Ex and Ey significant amount, both content, Ex component as well as Ey component. So, that time it will be called as a hybrid mode. But nevertheless, if you see the transverse component, that is Ex and Ey, if they are having different component, you can actually define which direction their combination may be electric field. You can transverse component of the electric field, you can write something like this, Ex, Ay. So, direction can be neither along x direction, along y direction, you should have components. So, other direction will be. So, that can be considered as a polarization. So, three parameters very important. That is a polarization, which field, which direction electric field is oscillating, amplitude that actually decides how much power associated with the guided mode, and EMXY, that is actually your profile distribution, that hardly matters as long as it is normalized, that profile is known. And then propagation constant and frequency, of course. Frequency means actually operating wavelength, it is decided by omega equal to 2 pi c by lambda. Okay. So, these are the parameters in your hand when you have a waveguide with some guided mode. If it is a single mode, you do not need to actually assign aim or something like that, just a fundamental mode will be guiding. Now, you see, you can actually modulate the polarization. Polarization you can have, suppose you have a x component and y component. Okay. So, what you could do, you can actually somehow you can change the polarization components. That means Ex fraction is, if you can just modify to higher level, and Ui fraction can be reduced to the lower level for a given power or amplitude of the electromagnetic wave, and then you can make it on off. That means you can rotate the polarization and you can sense the polarization at the receiver. By rotating the polarization on and off, if it is a digital communication, then you can actually encode the data, and at your receiver you can actually sense what polarization it is receiving. If it is just rotated polarization coming, you can say that is a 0, and if it is not, then it is a 1 if it is a digital communication. So, polarization modulation is one option for you. And then another thing is that amplitude modulation. You can have a modulator where as it propagates, somehow you can create certain kind of mechanism where amplitude can be reduced to give you a 0 data, or according to your requirement it can be higher value, you can get a 1, or of course you can get anywhere between 0 to 1 level if you can actually have some kind of mechanism that you can continuously any level you can get your amplitude. That is how you can get a amplitude modulation. And finally, this is a phase. As long as your omega is fixed, so phase modulation means basically you can say that beta m modulation. If you can modulate the beta value is nothing but beta equal to omega by c n effective. Somehow if you can just modulate the effective index of the guided mode for certain length of propagation z, it is given here. So, you can have certain phase modulation, and that phase modulation you can effectively detect, that can be through a circuit or something else. We will be discussing a little while later that how this phase modulation can also eventually help to give you amplitude modulation also. So, these 3 modulation mechanism one can choose, but for photonic integrated circuit purpose, basically polarization modulation is not preferred, because that is very difficult in case of particularly silicon, which is basically isotropic material. So, polarization modulation is discarded, not at all popular, not at all used for photonic integrated circuit purpose. However, this amplitude modulation and phase modulations are very popular for photonic integrated circuit applications. So, now we, as I mentioned, that amplitude modulation eventually gives you intensity modulation, and phase modulation eventually gives you frequency modulation. Also, if you just design your circuit in an interference, you can design some certain kind of interfering circuits, then you can convert phase modulation into intensity modulations. So, ultimate key is the phase modulation. If you can do phase modulation at a very high modulation speed, then that can be actually utilized as a encoding element or modulation, data encoding or data modulator, optical modulator, so called optical modulator. All right. Now, next thing, how that is done. For example, this is your waveguide, this your input and this is your output, and as it coming, as the mode coming, and you can consider a electric field, you can consider dominant electric field component. If that is Ex, that means E polarized, or it is dominant by Ui, then Ui you can consider. And then you can consider the amplitude. Profile you are not considering, that thing actually fixed as it propagates, we assume that is fixed, and amplitude that actually associated with the power of the guided mode, and then this one, this is your input, and you know as it propagates the phase, initial phase will be there beta z, as you consider z equal to 0 here at this point z equal to 0, that means we can consider, we start counting phase from here itself. Before that there will be certain phase, initial phase will be there, but as I consider this is my phase where I want to encode my phase for this length, L length for example, yeah, L length, somehow I want to do some certain kind of phase modulation. Okay, I am just discussing about phase modulation or frequency modulation. Why phase modulation is called a frequency modulation, that also I am going to discuss. So, now then after traveling this L length, it's supposed to have a phase of e to the power minus j beta L, because z equal to 0 here, that means beta L amount travels, because of the propagation you get this phase factor, right. In addition to that, if you have a time dependent, this is a kind of phase modulator, you have integrated here, that time dependent phase modulation can give here. So, in that case I can have omega naught t minus phi t, where omega naught I consider as a carrier frequency, or you can consider that say 2 pi c by lambda naught, where lambda naught is the operating wavelength, that is the lambda coming out of certain laser. It can be hybrid laser, it can be external laser and so on. So, this is the thing. So, if you have a phase modulation means you are changing your phase as a function of time. For example, according to your requirement you can actually design what type of phase modulation you want. Okay. For the moment I am considering that your phase is changing as a function of time. So, that means you, instead of normally any guided mode, when it is eigen mode, So, the time dependent part is omega naught t and beta jet we consider only space dependent part. But now phi t is coming. So, additional phase change is coming, that is also time dependent part is here. Okay. So, now let us consider a simple example. Let us consider this phi t is a sinusoidal. You are just giving a data or some modulating signal, so that phase is being modulated based on this one. We consider this omega m is the modulation frequency here. In this case, simple sinusoidal delta sin omega m t here, and you can consider this delta is equal to less than 1, okay, because normally if it is a fraction, then it basically it can little bit it can modulate the phase, whatever phase is coming you can modulate the phase. So, now you can consider maybe it is this is phi t is equal to this one. Now, capital phi t I defined as total time dependent phase omega naught t minus delta sin omega t. So, here I am just inserting delta sin omega m t, right. So, now if we do that little bit analysis, what we get? Normally we know that suppose you have a phase, time dependent phase omega t, we write phi t, what you get? That omega basically frequency, that means you can say that per second how much phase it can acquire at a particular point z equal to 0 for example, right. So, if I do d phi by dt, then ultimately you get omega, that means rate of change of phase gives your frequency of the guided electromagnetic wave. Now, your phase is now has additional part. So, if I try to find out frequency response d phi by dt, then you get, you see omega naught t goes and delta sin omega t omega m delta cos omega m t. That means just pi by 2 phase shift is there, and you have this is your frequency swing you can get. Instead of omega naught, earlier it was omega naught, now you get, because cos omega m t can go plus and minus. So, you can see that this frequency goes plus minus certain range. So, that means if you modulate with a certain frequency, then you can get your frequency actually you can get modulated also. That is why it is called frequency modulation. Phase modulation is equivalent to frequency modulation. Okay. So, now if you just see, now try to look into it. If you just analyze this one, it will be e j omega naught t multiplied by e to the power minus j delta sin omega m t. Let us look what is this, that is exponential, and then you have a sin omega m t function, that is actually again you are just representing with exponential term minus j is there, complex form, right. Mathematically if you look into it, it can be expressed in this form. Okay. You can have omega m t e to the power minus j n omega t, where n is the integer starting from minus infinity to plus infinity, whatever the integer values are there you can consider minus infinity to plus infinity, and you have a special function, so called Bessel function. This is called Bessel function, and that Bessel function is a special function. I will just going to give you that expression, but that value depends on delta and n. Suppose n equal to 0 and delta a certain value, you can find out what is the value of the, from the special function you can get, and e to the power j n omega m t. That means you are getting, this thing can be decomposed into combination of different frequencies, that omega m, then 2 omega m, 3 omega m, all this frequency component is there, and that frequency component is coming here. So, that means e to the power j omega m t, you can have e to the power minus j omega m t plus minus, and then you can have a plus minus e to the power j 2 omega m t, then it can have e to the power plus minus 3 j 2 omega m t, 3 omega m t, and so on. All these frequency component you can expect, right. So, that means ultimately you can get your frequency components omega naught plus minus n omega m. So, these are the frequency components you will be getting at the optical output. So, without this modulation of delta sin omega m t, if you do not have, if you block that, you certainly would get only e to the power j omega naught t, only one frequency you would be getting. But once you modulate with your some kind of sine omega t with a modulation frequency omega m, then at the output, optical output, if you see, you can have a multiple frequencies omega naught plus minus n omega m. N can be considered as 1, 2, 3, 4 and so on. So many frequency component you can expect, right. So, if you just do this one, this is what I have just tried to say, that omega naught minus n omega m, okay. This is j n omega naught, of course you have to write here t, okay. And normally propagation constant, because of the propagation whatever the phase comes, e to the power minus j beta L we have written here. Good. Now you check what is this spatial function, so called Bessel function. It is called as a Bessel's functions. So Bessel function, you know, n can go from minus to minus range to plus range, that is what it is defined here. So, but they have one relationship, they are somehow antisymmetric. J minus n delta equal to whatever j n delta you will be getting minus 1 to the power n. So, n equal to 1, if you just put j minus n delta, meaning minus j n delta, and if n equal to 2 minus 2 delta, that will be equal to plus. So, that is j 2 delta, no, this is 1, this is 1 I am writing, this is 2, then you will be writing j 2 delta. Again j minus 3 delta should be equal to minus j 3 delta. Again j 4 delta, j minus delta should be equal to plus j 4 delta. So, that means minus plus, that means only odd number, if you are just counting odd frequencies you are just considering, in that case it will be minus and otherwise plus. That means what I mean to say, that suppose certain delta, and for that you have j 1 coefficient is there and j minus 1 delta is there, both are there, but both frequency will be present, but they will be differ by minus 1, that means they will be pi phase shifted. So, if you have a frequency, this is omega naught, then you can get this is omega naught plus omega m, and this will be your omega naught minus omega m, but whatever the amplitude, this is your central amplitude of the electric field you are giving herein. So, that is there, and here you will be getting this one, some component you may get, but you will be seeing that whatever phase it is here, omega naught omega m, and this phase for the carrier frequency phase they are same, but the other one phase will be just opposite, this will be inverted. At any instant of time if you see, then this omega naught omega m component, that will have in phase with the carrier, but this component generated, that will be pi phase shifted. And here it is shown, if you just instead of delta, if you are just representing x, I have just copied from some internet, most probably from Wikipedia, you can plot also, there are function is there, Bessel function expression is there, based on that you can just plot as a function of x. If you see, that means delta, this value if you keep on increasing here, this is suppose delta you consider, right. So, j not delta, you see it is when delta equal to 0, that is maximum, and then it will keep on coming down and goes negative as you delta increase, then fine. But when delta is very small, then you can consider somewhere here, for example. So, j 0 will be some this much value. So, it will not go to 1, rather it will be going little later, maybe 0.9, whatever the values are there. Now, for same delta, if you see j 1 x, that will be this value, okay. This will be about 0.5. So, if it is 0.9, it will go up to maybe 0.5 or 0.5 here. No, I think it is less than 4. So, this can be 0.35, this can be here also amplitude, if I just writing 0.35 it will be there, because j 1 x equal to minus j 1 x, only amplitude will be different. So, both side you will get frequency components, but their amplitude will be almost 30% less than the main carrier coefficient, okay. So, you get actually whenever you are doing some kind of phase modulation with a sinusoidal function with a frequency omega m, then you can see all this side frequencies will be there, and then you can get also another frequency, that is omega naught plus 2 omega m, that will be here, and omega naught minus 2 omega m, that will be in phase. That means this one and this one, that will be in phase. But unfortunately, when delta is very small, if you just try to see what is the value of j to x you are getting, that will be somewhere here, right. So, it will be very less. So, that amplitude will be reduced. So, that means your frequency components will present, but that amplitudes will be reducing in fashion when delta is very small, smaller than 1. Hopefully, this is clear now. Now, you see, if you try to see analog modulation, that means this phi t can be a function of time with certain modulation like this type of analog modulation, not like that phi t is a step function, just a 0 or some values. Instead of that, as a function of time, it is changing. Your data can be, your incoming data, whatever data is coming, that can be also certain kind of any value it can take, for example. Based on that phi t also, it will be proportional to that data strength signal, whatever data you want to encode, depending on the strength, this phase will be also decided. So, suppose this is your carrier, that is actually omega naught, okay, that is the electromagnetic wave corresponding wavelength lambda naught, for example. Now, this is your modulating wave, which is actually relatively lower frequency, that is your data, you can consider analog data, this is there, right, this type of modulation if you are doing. Now, as you keep on changing your phase, right, as you keep on changing your phase, so that means your, this is your maximum, this is your delta value, and then plus delta, this way it will be oscillating like this. So, modulated results, what you will see, that at this point your signal, if you see that it will be their frequency will be actually such that the lambda will be, this is a function of t, for example. So, the lambda will be just squeezed and then relaxed, where depending on the value here, it will be just this type of modulation you can see, this time dependent the amplitude. So, the time period here reduced and relaxed, time period reduced, relaxed, time period reduced, relaxed. So, that is how depending on the, and it is not like step type, it is actually depending on the strength of this one you will be getting, the frequency will be modulated. Okay. So, that is what it is called analog modulation. Your frequency change is happening, okay, and that frequency change actually corresponding proportional to the strength of the sinusoidal power. Okay. So, frequency component changing, but if you just do Fourier transform, you will see what is the frequency, that whatever I mentioned, omega naught plus minus n omega m you will be getting. So, now digital modulation. So, digital modulation means what you can consider this phi t can be either say certain value 0 or some value pi, for example. Okay. So, this 0 and pi, that actually depends on your digital 0 or digital 1. Suppose 0 coming, certain phase is there, and then data when 1 coming, phase will be different. Okay. For example, here consider your carrier as a function of time, you see this one. Now, this is your modulated wave, say digital data, for example, your 0 bit, 1 bit, and then 0 and then 0, all these bit streams are coming, for example. So, when 0 is there, you do not see anything change, that means no phase change is happening here. So, that is why this portion is fantastic up to here, up to this portion. This is the portion up to here, it is okay. Now, when 1 is there, you see this thing actually somehow phase is shifted, because the presence of this 1 means certain voltage you are applying, for example. So, depending on the voltage, diffractive index is changing, and diffractive index changing means you have changed the phase. So, phase shift is happening. So, that is why it is, instead of going from this to this, instead of that some delay, it will be as if it is starting from here at this point of time. So, it is just shifted here. Similarly, when this is withdrawn, that 1 bit is gone, then again it will be again relaxed, instead of starting from here, it is actually as if starting from here. So, this is this region, if you see, phase revert, some phase shift is happening. So, that is how you can say that the digital data, whenever it is coming 1, that means you are getting a phase shifted signal. Depending on the height of this signal, you can have a driver, you can control the voltage, and controlling the voltage you can change the refractive index, and that phase shift can be added here during this period. And once this phase shift again withdrawn, then again it will be like a as usual waveguide structure. So, it will be again propagating like this. Again another one comes, that time again phase shift will be there like this, so on. Okay. So, that means you can have analog modulation, you can have a digital modulation, but challenge is that if it is digital modulation or analog modulation, your receiver photodetector should be able to actually detect the frequency change, or you should be able to detect the this phase shift basically, so called. So, now I will be discussing amplitude modulation or intensity modulation. So, that is so far it is very popular for photonic integrated circuit for optical interconnects. So, phase modulations are also popular, but phase modulation is used to get amplitude modulation or intensity modulation, so that your detection, particularly when you are detecting with a photodetector is a intensity detector, basically square law detector. So, it can actually easily it can see change in power. So, if it is digital communication, 0 and 1 means you can think of that power is completely switch off to 0, nothing is coming to the photodetector, that time photodetector will detect as a 0 bit, and when some current is there in the photodetector certain value, then it will see that okay, bit is 1. This is a simple example. So, how that is done? Let us consider a balanced Mach-Zehnder interferometer. We have discussed so many times before, I reproduced it again here for the understanding of modulator, particularly amplitude modulation or intensity modulation. Let us consider a balanced Mach-Zehnder interferometer constructed by Y junction, single mode waveguide here, Y junction, it splits into two amplitudes, amplitude splitting, just preserving the energy conservation also. So, A by root 2, A by root 2, AI is the amplitude coming in here. This we have discussed earlier, I am not going into detail why root 2 comes, and then as it propagates, you know, it will be A by AI by root 2 e to the power minus j beta L, as the propagation that beta L length, that phase will be there. Similarly, A by AI by root 2 e to the power minus j beta L, as long as it is balanced, that means this arm and this arm same, they are balanced Mach-Zehnder interferometer, this part will be same for both the things. And when comes here, combines here, then again A by root 2, AI by root 2 will club here with additional 1 by root 2, and then plus AI root 2, this one, that will again additional 1 by root 2. So, what will be getting? You will be getting AI. So, that will be actually equal to A naught, that is what we discussed earlier. So, here reproduce that thing. So, A out will be this one. So, that means if it is a balanced Mach-Zehnder interferometer, whatever input power you are giving here, same output power you are getting here, as long as you consider that the waveguides are lossless, junctions are lossless. Okay. But if waveguide losses are there, and if this length is suppose say length is L, that means e to the power minus alpha L, amplitude loss will be there, that means A naught will be equal to AI e to the power minus alpha L, that means amplitude, and power loss will be P naught, P output will be Pi e to the power minus 2 alpha L, because power is nothing but we according to our convention, that is A naught star, A naught and A naught star. Okay, complex conjugate you have to take, along with that you have e to the power j omega t, so on, that is complex conjugate will cancel. So, that is my 2 times multiplication, that is why minus 2 alpha L. So, alpha is the amplitude loss coefficient, 2 alpha is the power loss coefficient or intensity loss coefficient. But for the moment we are considering it is a lossless case, anything loss is there, you have to calculate accordingly. So, now you see, suppose in a balanced Mach-Zehnder interferometer you have a phase you are adding here to this mode in the upper arm, which is time dependent, and this phase can be changed in terms of voltage, time dependent voltage or time dependent current. That is eventually can be your analog signal or digital signal. As a function of time, voltage can be fluctuating depending on the data, current can be fluctuating. So, depending on the mechanism of this waveguide structure and your design of your modulator, phase modulator, you can, that phase can be either modulated because of the applied voltage or because of the current flowing through it across the waveguide structure. So, phase can be changed. So, if that type of phase is changed, then what you can say that upper arm whatever coming out function of time phase has to be included. Then what would be A naught? If you have some time dependent phase is there, let us see what it is. You see A naught equal to, the first thing is that this one I am writing AI root 2 1 by root 2 when it is coming here, and then second term this one AI by root 2 1 by root 2 times, and then your phase factor it is there. Now, it is simplify. So, that this term will give you AI by 2 and this one will be giving AI by 2. So, AI by 2 is common, then first term will be 1, second term will be this one, e to the power minus j phi t. Now, what you do? Simplify it. You take AI by root 2, this one I am just writing directly here, and then I take a common factor e to the power minus j phi t to phi t by 2. Then within box I can write this one e to the power j phi by t, because this one if you multiply then you will get 1, this one you multiply then you will get this one. This is just for simple simplification purpose. Then you see this is like e to the power x plus e to the power j x minus e to the power j x, that is nothing but 2 times cosine x. Okay. X is equal to here phi t by 2. Okay. So, now what we do here, I am writing here A I by 2, because A I by 2 is there and this 2 will come, that gives you A I, and cosine x and times this phase factor. So, this will be phase factor and this will be your amplitude. So, amplitude will be now time dependent. It is a cosine function, cosine phi t by 2. Along with that you get additional time dependent phase, right. So, amplitude modulation as well as phase time dependent phase modulation you are getting here. But if you try to see what is the power, that means you have to take A naught and A naught star. If you take A naught and A naught star multiplication, that is to give power, that should be proportional to AI square cos square phi t by t, that is the thing, and this one will be complex conjugated to be e to the power minus j phi by 2 e to the power plus j phi by 2, that will be cancelled. Okay. So, ultimately you are getting intensity modulation. Okay. So, what you get if you have a phase modulation here, then at the output you get amplitude modulation as well as phase modulation, but once you try to detect with the modulator, then a photodetector, sorry, then you get only power modulation, amplitude modulation or intensity modulation. Okay. This is a very popular structure, that you use a balanced Mach Zehnder interferometer, you whatever phase required you just introduce in one of the arm, and depending on the phase you can get your output intensity modulated accordingly. So, that can be analog, that can be digital. Okay. So, if you have a digital signal like this, so you have 0 here, V equal to 0 if you are giving here, or you are giving some voltage V, that is actually corresponding to phase difference of pi if you are giving. Two phase either 0 or pi you are choosing as a data 0 1 coming here to modulate this section for of your waveguide. Then what you get? Let us try to see that upper arm you get e to the power minus j phi, phi can be again 0 or pi. Okay. And this one nothing is happening, only propagation length, that is common to both the arms. So, I am not considering there. And what would be the A naught? Let us see, same formula we are using, instead of time dependent we are using phi to digital value either 0 or 1. So, 0 or pi. So, if it is 0, then your power will be phi equal to 0, that means your power will be just exactly pi. If phi equal to pi, then your power will be just pi. Pi by 2 equal to cos pi by 2 equal to 0. So, that means your this power actually here can reproduce 0 or pi. Whatever 0 your electrical signal comes, that will appear as a 0 and high power and low power as a light output power. But when you are getting 0 here, no light is coming out here, that means the optical 0, that time light is actually basically getting lost in this section. Okay. I have discussed that how that is actually lost there, because it is a single mode waveguide. Here you can assume that it is like excitation of higher order mode, and that can be dissipated here. So, that means your digital electrical signal can be converted into optical digital signal. Okay. And then you can, since it is optical, so you can use your optical waveguide or optical fiber for transmission, data transmission. Now, another type of modulator we normally use, that is actually, for example, when we discuss this thing here, your this AI can be multiplied by e to the j omega t minus beta j so on. So, here omega or lambda can be anything, any lambda you can choose, because identical arm is going, ultimately your desire is that you get either 0 phase shift or pi phase shift. Okay. So, that is how you can get your output, lambda can be independent. Now, we can, there are some issues are there to have a very good high speed amplitude or intensity modulator using balanced Mach Zehnder interferometer. So, that is the reason people modified this Mach Zehnder interferometers little bit differently, so that your design issue will be, particularly intensity or amplitude modulation will be easier, but your device will be operating only at one wavelength, or just kind of certain set of wavelengths. This type of structure also I have discussed earlier. So, it is basically a unbalanced Mach Zehnder interferometer, 3 dB power splitter, and then you have unbalanced means the upper arm having a length L1, which is certain L0 plus delta L by 2, and lower arm L2 equal to L0 minus delta L by 2, such that L1 minus L2, this is a lower arm length, this is upper arm length, L1 minus L2 equal to delta L. And you know that if you just see what is the transfer function for this one, that we have derived earlier also, that in the cross port, if you are launching here, in the cross port means here PC whatever you will be getting pi cos square beta delta L by 2, where beta again you know, beta is nothing but omega by c n effective, right, beta delta L by 2, and bar port what you supposed to get here, that will be sine square, and here beta whatever I have written here, it is written down here again 2 pi by lambda n effective lambda. And you know, then free spectral range, that means you know, if you are just changing that, because this is beta is actually wavelength dependent, that means this type of phase condition, for example, beta delta L by beta delta L by 2, if it is actually pi by 2, then you supposed to get cross port 0. If that is 0, then cross port you will be getting just exactly the pi, right. So, this pi by 2 again depends on beta, which is actually nothing but 2 pi by lambda n effective. So, that means you can have a, basically you can consider 2 pi times 2n plus 1 integer. So, that means a series of lambda, successive lambda with a certain separation, they will be actually giving you 0 output or maximum output at the cross port or bar port, because cross port and bar port they are cosine function and sine function. And those wavelengths which are giving maxima here or minima at the cross port or bar port, their separation in frequency FSR delta nu FSR, if you just consider delta nu FSR frequency domain free spectral range C by Ng delta L, that also we have derived earlier, just reproduced here for the completeness. Similarly, delta lambda FSR, if you just consider instead of delta nu FSR just delta lambda FSR, then lambda square by NGL. Ng is the group index, nothing but n effective minus lambda dn effective by d lambda. All these we have discussed earlier, just reproduced here to understand how this type of structure can be useful for modulation, intensity modulator. Okay. So, we have just simulated for a certain waveguide structure, where waveguide width, you know, this type of waveguide you consider in silicon, this is W and this is H and this is a small age. So, if you are considering W equal to 500 nanometer, device layer thickness equal to 220 nanometer, small h equal to 90 nanometer, and gap G, this G age means when you are designing a directional coupler, that gap is you are considering waveguide to waveguide separation is 250 nanometer, and this delta L equal to 450 micrometer is considered in this example, and L 3 dB, if you are considering this gap that 3 dB length of the directional coupler is about 5 micrometer, that is calculated, and if you assume that overall loss of the waveguide is about 5 dB per centimeter, then transfer function cross port and bar port, you know that cosine function and sine function. So, cos port beta delta lambda equal to 0, then you are just getting this one, this maxima, then periodically it is going like a cosine function, and this will be going like a sine function, it is going like in the bar port, and you see this is plotted as a function of lambda. So, when I say that this delta lambda FSR, that I mean this to this separation, okay. This is actually the wavelength separation, that is called free spectral range, okay. And if you just consider in the dB scale, you see normally it is not going up to the 1 level. That means input power is a consider, say for example, it is a 1, but at the output neither in the cross port nor in the bar port it is going to the level of 1, because there is a loss I have considered in the waveguide structure in your simulation. The standard Mach Zehnder transfer function you can use, and you can just plot this one using your simple MATLAB program, then you get. And dB scale, if you see cross port, this is the blue curve, and bar port, this is the red curve. You see it is in the dB scale, if you see that there is a extinction when this certain wavelength supposed to be minimum, that is not going up to the level whatever about more than 80 dB is going for the cross port when it is minima coming. This is because this is unbalanced nature, you can get this one. But nevertheless, you get extinction about minus 20 dB even in the bar port, and cross port you can go very high, that is fine. But you can design such that both cross port and bar port you can adjust the wavelength, waveguide losses etc., so that you can get both the arm similar type of extinction, that is possible. But for the moment let us concentrate only on one output. So, if you just take from 1520 to 1580 nanometer over 60 nanometer, periodically you get see in the one of the output port you are considering, for example, in the cross port or bar port you are considering, right. So, you see this one that this is the thing 1520 to 1580 nanometer you are considering. You little bit zoom in around 1549 at this region, you zoom in, then you get this is the output 20 dB. So, this is considered as a bar port, for example, right. So, this is about 20 dB considered, means it is actually in the bar port. So, we are just following in the bar port output. If you are launching here, that means this is your bar port, this is your cross port. So, bar port transfer function that will follow here this function, and because you are using a some kind of phase delta phi here, okay, because that will be this delta phi you have to control for your data purpose. So, if delta phi equal to 0, then you get this type of transfer function according to the all the other parameters given here. Now, you zoom in, you get this one, and when you get this one, you see this is the delta phi 0 curve. Now, if you give a little bit of phase shift here delta phi 0.73 pi, then this transfer function will move to this one. Now, suppose your lambda operating wavelength is set here around 1550.5 something here lambda. So, when no phase is there, you supposed to get laser power up to here. This is your output transmission. But when this delta phi comes here, then transfer function moves, your transmission drops to here. That means you can have your output this level to this level. So, when there is no phase, you are supposed to get a power level here, transmission is close to 0 dB, that means normalized one. If it is 1 milliwatt, close to 1 milliwatt, input is 1 milliwatt, close to 1 milliwatt you are getting. But whenever you are just tuning phase here in one of the arm, then your power transfer function is moving, then you are getting drop. So, you can, if you can tune delta phi between 0 to this much phase, 0.73 pi, then your power can go on off like this. So, it can get a intensity modulation, but you can find out what is the phase for if delta phi is corresponding to 0 bit and delta phi corresponding to 1 bit. This 1 bit, the voltage height, if you are just considering this is 1 bit, this voltage height should be sub voltage or current flow or whatever should be such that it should give at least 0.73 pi phase shift. Then you can get this type of intensity output at the bar port here. So, that will be a digital modulation. Okay. So, similarly, similar type of design one can get, you can this kind of wavelength selective intensity modulator for all pass micro ring resonator. We have discussed also the transmission transfer function, amplitude transfer function, beta L or L is the perimeter length and this is the round trip things, and this is the intensity transmission here, that is actually nothing but B naught by Bi, B naught by Bi, and then take their complex conjugate, then you get a power transmission or intensity transmission. Beta again redefined, and here we consider this is the throughput coupling and this is the cross coupling T. So, that we assume that it is a real, that coupling coefficient is real and R square plus T square equal to 1, and loss factor A we defined already when we discussed about micro ring resonator to minus alpha L, just reproduced here to show that how micro ring resonator also can be useful as a photonic integrated modulator. So, now you see we know that at resonance condition transmission will be this one where beta L equal to 2 pi times integer, m equal to say 1, 2, 3, 4 so on. And we know that also for a ring resonator this delta nu FSR free spectral range for the ring resonator C by NGL and in terms of lambda, lambda square by NGL, that we know that earlier. Okay. Now, you see as a if I consider the input here, you are just considering 0 dBm or 1 milliwatt power. 0 dBm is equivalent to 1 milliwatt, just 1 milliwatt you take log scale. So, then you get 0. So, because milliwatt we consider this 0 dBm, I think all of you know that how to do that. And loss again we consider the waveguide loss is about 5 dB per centimeter. Nowadays waveguide loss can be reduced to 1 dB per centimeter as well. Okay. So, transmission characteristics if you see, this is extinction is coming down to less than minus 20 dB everything, and at resonant wavelengths this is the FSR, so called FSR, as long as lambda dependencies you are considering, this is the transmission of resonant, almost everything is coming out here at 0 level coming out. Yeah. Okay. dBm scale we are showing here. So, now if you see you have a phase shifter here for example, you just consider a phase shifter, right. So, this phase shifter if you add only 0.04 pi, then your transfer function actually tuned from this wavelength to this wavelength. Again if you just choose, if you are choosing your lambda operating here at this wavelength laser, now for 0 phase here at this point your output level is this one, and if you are giving this much pi, output level will be coming down this one. So, that means on off will be this to this level. So, minus 20 dB to almost 0 level you are getting. So, that is actually almost 90%, 0.9 dB less from 0 to point insertion loss we are considering this much. So, from 0 to here maybe minus 0.9 dB level you are getting, depends on your choice of your lambda. So, that is actually insertion loss. Insertion loss is nothing but actually log of 10 P output maximum by P input. So, when you are maximum getting here and whatever you just normalize to input, that is called insertion loss, and extinction loss is actually your extinction ratio, not loss, extinction ratio is actually 10 log of 10. So, P out max by P out minimum, that is actually called extinction ratio, that is 19 dB. Okay. So, I see that same thing we discussed about your in case of here. So, it is almost similar type of thing, insertion loss is about 1 point, similar type of waveguide structure we consider, same type of delta L we consider in the unbalanced arm, that the difference in arm length, and micro ring resonator also we consider the ring resonator length 450 micrometer. So, FSR is almost similar. So, this FSR we consider about 1.6 nanometer or about 200 gigahertz in frequency domain. That is the ITU channel normally we use, that any ITU channel if you use, and at this around this wavelength, that will be intensity modulated with extinction ratio of 18.7 dB. But one thing is considered, speed, how fast you can switch this on off, that actually depends on your how fast you can encode your data. That means this delta phi change you need to do how fast you can do. Faster you can do, your data encoding will be very fast. So, you need to find out what is the technology problem, what is the material related problem, what limits this speed. That is most important part of the modulator design, especially for photonic integrated circuit when you are talking about CMOS compatible silicon photonics. So, I will be discussing later on what are those mechanisms in future classes, what are the modulation mechanisms, how this delta phi get changed from 0 to certain value. That depends on your applied voltage into the waveguide or certain amount of current flow into the waveguides, carrier change or whatever. What all those mechanisms are there, we have to discuss first, and then how the speed is limited, how much maximum speed you can achieve by a certain design of modulator structure. So, here today we have discussed that waveguide design, what type of architecture, device architecture we can use for your amplitude modulation or phase modulation, and later on I will just come back to discuss about what are those mechanisms and what are the speed limit and how you can achieve a maximum possible efficiency, figure of merits, compactness, and also required voltage, lower voltage or higher voltage, as small as voltage required is good, and all those type of things we will be discussing in the future classes. Thank you very much.